Wonderful. Thanks very much, Kelly, for that warm introduction. Hello, everybody. I'm reaching you here from Toronto. And if someone can just give me a message that you can hear me okay.
Yes, we can. Yes,
Okay,
go on.
wonderful. Thank you. All right, so I'm going to jump right in, and I'm going to offer a perspective here on machine intelligence from the vantage point of economics. I'll make 3 points this afternoon for you.
Yeah.
The first one that I'm sure most people here are familiar with is that there's no ghost in the machine. AI is computational statistics that does prediction. I think what has drawn so much attention is that it's more powerful. This form of prediction is more powerful than most of us had imagined. So we define prediction as taking information you have to generate information you don't have. So, for example, people are familiar with the information I have are 30 years of historical sales data, and the information I don't have are sales in Q3 next year. That's the thing I'm trying to predict. But of course, prediction in this setting, it's multimodal, and so it also includes things like the data I have are the pixels in a medical image, and the data I don't have are the labels on the tumors as malignant or benign. And that's also prediction. And once we started realizing, for example, that type of problem was a prediction problem, then we realized that ultimately, for example, image recognition, vision systems, that machines could see. And when machines could see, that enabled things like cars that can drive themselves. So from an economics perspective, the way we think of the rise of AI as a drop in the cost of prediction. So as AI becomes more and more powerful, the quality adjusted cost of prediction drops. And so going back to economics 101 and downward sloping demand curves, that when the cost of something falls, we use more of that thing. So how will we use more prediction? First of all, everywhere that we're already using prediction, we'll use more of it. It's better, faster, cheaper. So, for example, in many banks hired before the rise of machine learning, were hiring a lot of data scientists, and they were doing predictive analytics for tasks like fraud detection, anti-money laundering, sanction screening. And so when machine intelligence came along that lowered the cost of prediction, we simply took out some of the old predictive analytics systems and we replaced them with new predictive analytics. So that is, in terms of the downward sloping demand curves, prediction getting cheaper, we use more prediction. The first way we use more prediction is everywhere that we're already doing prediction, we now just start using more of it. But there's a second way that we increase our demand for prediction, and that is we start turning problems that we didn't used to think of as prediction problems into prediction. Just like we did with prior technologies. So, for example, with semiconductors lower the cost of arithmetic. Our first application of semiconductors was in areas where we were already doing arithmetic, and now we could just do it better, faster, and cheaper. So in the United States, examples of that were organizations like the Pentagon, NASA, the Census Bureau. They all employed people doing arithmetic, and they were the first adopters. But then as the cost of semiconductors fell, we started taking problems that we didn't used to think of as arithmetic problems, and we turned them into arithmetic. Canonical example of that is photography. We used to think of photography as a chemistry problem. And as arithmetic became cheaper and cheaper, we transitioned to an arithmetic-based solution to photography. And now, of course, we're doing the same thing with AI and prediction. Canonical example of that is driving. I suspect many people at this conference would not have characterized driving as a prediction problem even as recently as 10 years ago. Whereas today with artificial intelligence, that's precisely how we're solving it. And many of these other types of problems are also being solved as prediction problems. We are turning these all into prediction problems so that we can use machine intelligence. Now, if we were having this meeting last year, on this day last year, November 13, even the experts in the field would probably not have thought that we would be able to solve one of the foundational problems with prediction, and that is language. But of course, on November 30th, when OpenAI introduced ChatGPT, even people that were working in natural language processing, I think most of them were surprised at how well this technology seemed to function. In other words, as everybody in this room probably knows, these language models are simply computational statistics doing prediction. We give them a series of words, what they call tokens, and then they predict the subsequent series of words that would follow, as they have in this example here. So these language models, these LLMs, are simply token sequence prediction machines. So, what's interesting is the types of these models shifted significantly. I'm a professor at the University of Toronto in Canada, and in 2012, a professor at Stanford, Fei-Fei Li, was organizing a conference in vision systems called ImageNet, and a few students from the University of Toronto went to compete in that contest and demonstrated for the first time in a setting like that the power of a new technique called deep learning. And you can see on this chart, the vertical axis is a measure of compute, that in 2012 is the year when the slope of this curve changed. And we started building much larger models because these deep learning models were so powerful. And that's what happened with language. So here the vertical axis is number of parameters in the model. You can think of that like compute. And what I've circled are the early language models. Elon Musk recruited one of my colleagues, a person named Ilya Sutskever, to head research at OpenAI. And so he sent us the model in 2018, the first GPT, and then he sent us the second one in 2019. And then halfway through 2019, Microsoft made their investment into OpenAI. And the team there turned around and used this investment to effectively make a very big bet on what kind of capability enhancement they could get if they increased the size of the model. How much? Well, they put almost the entire investment into compute, and this is what they did. So those first two circles on the left were the original GPT-1 and GPT-2, and then the pink arrow is when they received that investment. And then the model in the very top right is the substantively increased size of the model that became ChatGPT. Now, what's I think very interesting is everything here is in the digital world. So when we're dealing with these language models and many of the AIs that people are talking about, they're all digital, occurring in the digital world. But if you look back at the first model I circled, the GPT-1, that's really the stage that we're at for a new kind of model, a new kind of foundational model. So just like the language models like Bard and ChatGPT are foundational models for language, we're now moving into a new world of creating foundation models for the physical world. And so there are a handful of companies working on these, such as this one, this is Toyota Research Institute, making these, instead of an LLM, a large language model, they're making large behavioral models. And so in this particular case, they have trained 60 skills on these robots in the physical world, and they're expecting to get to 100 by the end of the year. And then you can see the same kind of nonlinear growth, thousands by the end of next year, and so on. And so it reminds us of this curve of exponential growth, but rather than in the digital world, in the physical world. And the way that you can think about how these are being put together is, if you were to think about all your friends and all the jobs they do, and you were trying to decompose all of their jobs into the different tasks that they perform, which is a way that economists have been studying automation, is by breaking things down into tasks. You would probably say there are thousands and thousands of tasks that your friends perform in all of their different jobs. So if we decompose jobs down to tasks, we get thousands and thousands of different tasks. But here's what's interesting. If you then decompose every task down into what we call primitives, or you can think of them as verbs and nouns, we get to a very finite small number. So in other words, the many tasks are composed of a reasonably small finite number of verbs. And so what these behavioral models do is, just like the language models predict sequences of words or tokens, the behavior models predict sequences of verbs and nouns. So that you can give it a task, like, for example, you ask the robot, can you please unpack the boxes and put the tools on the shelf? They'll receive that command, and then they will predict the series of verbs and nouns that are required in order to perform that task. And so there's a variety of different companies that are doing this. This is one that I know about. I'm actually on the board of this company. It's a Canadian company. This build humanoid robots. And it's becoming a class. So this is a new category, like a new category of investment. And one of the reasons that these physical applications of artificial intelligence are attracting so much attention is because of the shortage of labor and the relative cost of machines with an AI cognition system relative to people. And so probably the most prominent company in this category is Tesla. Now, many people think of Tesla as a car company, but the founder or CEO does not. He thinks of Tesla as a robot company, that the Tesla cars are robots on wheels, and that the control system that drives the car is effectively like a cognition system for that robot. And Tesla is making their own humanoid robots. And he said at their last shareholder meeting, so their humanoid robots are called Optimus. He said the Optimus is extremely underrated. People just cannot comprehend the consequences. The actual demand for something like Optimus, that's these humanoid robots, might be 20 billion units, a number vastly in excess of the number of cars. My prediction is that Tesla's long-term value will be Optimus rather than cars. And that prediction I'm very confident of. Another person, Vinod Khosla, he's one of the most prolific investors in artificial intelligence. He's based in California. And he also commented that the thing nobody talks about is that in 10 years, we'll have 1 million bipedal robots, and in 25 years, we'll have 1 billion. You'll buy yours for 10,000, and it will be as important to your life as a smartphone is now. And then just last week, or about 10 days ago, China announced that they were going to make very aggressive investments in this category as well. Okay, so that's the first point here, is that prediction, AI is just prediction. There's no ghost in the machine, but prediction is much more powerful than we thought. And we've certainly seen that recently with all the increased attention to language models. And coming down the pipe are similar foundation models, but now for behavior in the physical world for these robots. That's point one, is prediction. Point two is that and what we're observing when we study companies that are making their AI strategies is that there's two components. There's what we call lane one versus lane two strategies that they develop predicated on AI. So you can think of lane one strategies as integrating AIs into their companies, where they have a system. Like, think of a bank. A bank has a system of how it operates. And there's one step in the system where they do predictive analytics, let's say fraud detection in a banking process. And so when they take out the old predictive analytic tool and put in the new AI, but the rest of the system in the bank stays the same, we call that a lane one strategy. So lane one is the system stays the same, and there's just a replacement of the predictive tool. We call that a point solution, a lane one strategy. Now companies are leaning into what we call lane two strategy, and that's what the book that Kadri mentioned is about. And so, to give you an example, this is a photo. We think this is one of the most important photos in artificial intelligence right now. This is a photo of people who are studying to get a license to drive a taxi in the city of London. So in London, in England, you need to go to school for 3 years to learn what's called the knowledge. And they spend a year studying maps, a year on mopeds driving around London, and then a year doing maps and mopeds, and then they get an exam. And the exam will ask a question like, you pick up a passenger at 4 o'clock on a Tuesday afternoon, and your passenger wants to go from the Churchill War Rooms to the Royal Botanical Gardens. What's the fastest route? Now, of course, today, you or I can use a navigational AI that will predict the best route between 2 points, and we can navigate the city just as well as a person who's gone to school for 3 years. And so how can that technology be deployed? One way is a point solution. So a point solution in this case would be, for example, to license the technology to taxi companies, and they give a tool to their drivers, and it makes their drivers more productive. And some of our colleagues, some economists in Japan, did a study to measure how much more productive, and they measured that the less experienced drivers got about a 7% productivity boost, and the more experienced drivers got a 0% productivity boost. They were already very good at navigation. A second approach is a system solution. So a system solution is one where rather than making a professional 7% better, we can go to amateurs and enable them to navigate a city like a pro. And so everybody's seen this example, or one of the others like it, something like Uber. So in the United States, before Uber, there were about 200,000 people that drove limousines and taxis in the United States. And today there's about 4 million people that drive for Uber. And so you can imagine that if each driver, let's say, brings a $25,000 car onto the road, and there's 4 million of them, that's about $100 billion in capital expenditure that's brought into the transportation system in the United States. And Uber wouldn't work without a navigational AI. So in other words, the navigational AI unlocked the capacity to allow people that had no training to navigate like a pro. And so they used that unlock for a complete system redesign. That's a lane 2 strategy, a system redesign. Here's the final point, and this is regarding these AI strategies that have both lane 1 and lane 2. Many people compare artificial intelligence to electricity. They say AI is the new electricity. So I'll offer the final example here from the electricity industry. That electricity was invented in the late 1800s. And in the United States, about 20 years after it was invented, there were still less than 3% of the factories in the United States had adopted electricity. The value proposition at that time for adopting electricity was that it could reduce energy costs, input costs. So for example, if you were using oil lamps to light your factory, that you could save a little bit of operating cost if you adopted this new technology. But many people, in fact, almost all of the factory operators did not want to tear apart their existing factories in order to implement electricity. So the ones that did were entrepreneurs who were building new factories. And even then, most of those entrepreneurs did not want to experiment with this new technology. So just a few very brave entrepreneurs decided that they would try using this new technology. So a factory at that time, this would look something like this. And when the first entrepreneurs tried using electricity, this is what they discovered. You can see in the top left corner of this image are these long steel shafts. So there'd be some kind of power source outside of the factory, like steam or water wheel or something. And that would turn that steel shaft. And the steel shafts would turn the wheels, and the wheels would pull the pulleys, and the pulleys would power the machines. And you can just see all that by looking at the picture. And so the first entrepreneurs that tried building with electricity, what they noticed was because they now had these cables coming in bringing electricity, they didn't need the steel shafts. And because they didn't need the steel shafts, they did not need those big, thick timber columns that were supporting the steel shafts. And so once they removed the timber columns, they realized this was much cheaper construction. This was much lighter weight, cheaper construction, because those timber columns had to be very thick and heavy in order to support the heavy steel columns. So in addition to lowering their operating costs, they now also realized they had much cheaper construction costs. The second thing they noticed is you can see that that steel shaft is so heavy that it's supported about every 10 feet by those columns, and everywhere the steel shaft is rubbing against the support, it's losing energy due to friction. So that meant that the steel shaft could only be so long. If it had too many supports, it would lose all this energy to friction. Once they got rid of the steel shafts, they realized that they didn't have to be limited in the width of the factory anymore. And because the factory was limited in width, they were building them vertically, so they would have vertical factories. Now that they were no longer limited in the width, they could build single-story, much larger footprint single-story factories. And so they realized that was a lot cheaper to build as well. So they lowered the cost again now by building single-story. After a few entrepreneurs built these single-story factories that were much longer footprint because land was cheap, they then asked themselves, why are we still organizing our factories the way we did when they were vertical? And so they transitioned to a complete redesign of the layout of the workflow. So the organization of people, materials, and machinery. Now that they had a much longer factory floor, they could do a total redesign of the system layout. Many of the factories experienced a sharp increase in productivity, 3, 4, sometimes 500% productivity increase. Finally, the last thing here is that you can, in those days, the machines would break down quite frequently. And you can see by looking at this image that when a machine breaks down, the entire factory stops because the whole thing is connected. They're all connected up by the pulleys up to the shaft. Now that each of the machines had its own electric cable and its own motor, when one machine would break, the rest of the factory would keep on operating. Again, they saw a huge productivity lift because of that. So the point here is what they realized in the beginning, the first few adopted it because they thought they could save some money in operational costs. But once they really got going, they just learned that was just the tip of the iceberg. That what this really did was it allowed for the decoupling of the machines from the power source. And once you could decouple the machines from the power source, you could have a complete system redesign. And that is precisely what we are anticipating to see coming down the pipe with AI. In the beginning, we see these point solutions, which is just keeping the system the same, but adding an AI like in the fraud detection case for banks. But what we're now seeing as we're watching companies make these investments is now many of them are planning for system level redesigns because they recognize that with AI, it allows them to decouple the two foundational things that happen in our minds anytime we make a decision or take an action. That's prediction and judgment. And what the AI does is it allows us to pass off the prediction. Instead of doing prediction in our own cognition system, we pass that over to a machine. And now we, people, just do the judgment. Machines have no judgment. AIs have zero judgment. And I won't get into it here, but in our book, we have a very formal definition of what a judgment is, like a mathematical description of judgment in a decision-making process. So the key point here is AI allows us to decouple prediction from judgment, and that allows for a total system redesign. So in the case of electricity, if the adoption rate had continued the way it was going, it would have looked like this pink line. But instead, once they learned that electricity didn't just lower the cost of inputs, that it enabled a total system redesign and effectively transformed many industries, that the adoption curve changed its shape. And we think we're in a similar moment with artificial intelligence, that we're the equivalent around 1900 for electricity, that in AI, we are starting to see a much greater level of investment as people realize that this can unlock system redesign. So those are the 3 takeaway points. I think I've used my time, and so I'll conclude there. Thanks very much.
Thank you, Ajay. This was fantastic as always. So I only can have one question for you. So actually, we have been discussing with you that issue before, and you have been quite pessimistic about the future of AI. And we just had our investor and philanthropist Jan Tallinn, who is one of the early investor of DeepMind and coming from Kazaa and Skype team, etc. And basically, his message today was that we should slow down and consider more the decisions we are doing with AI and the policies. So, what would you have to see to make you feel more optimistic about AI applications in society and impact?
Sure. Well, thank you for that question. I think I would agree with part of it, and I have a different view on the other part. So the part I would agree with is that we need much more effort and investment in safety and policymaking. So that part I 100% agree with. The part that I'm not sure that I agree with is slowing down. And there are so many benefits to machine intelligence in terms of what it can do for society. I'll give you one example. I think probably in the medium term, the biggest societal benefit that we will get from artificial intelligence will be applications in healthcare. Healthcare is very expensive, and in many of the OECD countries, we have aging populations. So we have a large bulge in the population that's about to begin retiring, and it's going to need a lot of healthcare, and we can't afford it. And furthermore, because healthcare is expensive, it's not equally distributed. And so in many countries, lower income people get less healthcare support. And what AI can do is, in particular, at the front end of healthcare, which is in diagnosis, and especially early diagnosis. That's where AI sweet spot. That's healthcare diagnosis is a prediction problem.
Yep.
And so AIs offer the opportunity to do very low cost diagnosis that is much more accessible than current methods. And the fact that we don't already have it is costing lives. In other words, it's not like it's marginal in the sense, the health economists who have studied AI and health have made some quite shocking estimates of how many people are either suffering or experiencing loss of life due to the absence of AI applications, including some that are already developed and just not yet deployed due to regulatory barriers. And so it feels like there are certain problems. Of course, climate is another domain where AI can have a big impact, and we need more, not less, and we need it faster, not slower. So I fully appreciate the trade-off, and I recognize that we're racing into a world that nobody fully understands. And so the question we have to ask ourselves is, do we think the benefits outweigh the costs? And right now, it feels like, I've been working in this domain for about a decade. And for the first 8 years or even 9 years, it was much less attention on this field. And many people were focused, a very small fraction of people were paying any attention, and they were mostly focused on the positives. In the last year, everyone has started focusing on the negatives. And it feels like the pendulum may have swung the other way. And so we need to find sort of, the right balance. In my view, the right balance is investing much more in safety, transparency, and policy, but not at the expense of investing less in its development.
Fantastic answer. Very optimistic for me to end here with Ajay. And Ajay, please don't leave.